Ciencia y Humanismo en la Academia Mexicana de Ciencias.
Buenas tardes, yo soy Graciela Raga del Centro de Ciencias de la Atmósfera y estoy encargada de presentar a la ponente plenaria del día de hoy. Realmente es un placer para mí y un honor presentar a la doctora Susan Solomon. La doctora Solomon es una de las científicas más reconocidas a nivel mundial en nuestra comunidad. En particular en su trabajo de atmosférica. Ella ha realizado investigaciones de frontera en un número enorme de temas, pero lo que quiero mencionar en esta presentación, en lugar de leer todo su currículum, que es muy extenso, es mencionar su trabajo pionero sobre la estratosfera polar en relación con la formación del hoyo de ozono. Sus estudios dieron como resultado publicaciones y premios, pero lo más interesante es que hay un glaciar en la Antártida que lleva el nombre de la doctora Solomon, y es una de las cosas que muy pocos científicos en nuestra área podemos poner en nuestro currículum. La doctora Solomon es miembro de la Academia de Ciencias de Estados Unidos, de la Academia de Ciencias de Francia como miembro externo y de la Academia de Ciencia Europea. Ha recibido numerosos premios, como les mencionaba, incluyendo la medalla Carl Gustav Rossby, que es el reconocimiento más grande en el área de ciencias meteorológicas, otorgado por la American Meteorological Society. Y también ha recibido la Medalla Nacional de Ciencia de Estados Unidos. Entonces, personalmente, para mí es una figura muy inspiradora por su trabajo y siempre la he considerado como un modelo a seguir. Entonces, por eso digo que es tanto placer que me da que haya aceptado venir a esta reunión de la Academia de Ciencias. Les dejo a la doctora Solano.
Thank you very much for that lovely introduction. I think it's a good thing I didn't understand everything, because I probably would have been terribly embarrassed. But I think I understood enough, and thank you. It was very, very nice. Well, I'm really very flattered and honored to have the chance to speak to you today. It's a very wonderful opportunity to talk to a broad range of scientists about issues having to do with how the climate system works and how it's being impacted by our activities. What I'm going to try to do is to talk about some of the factors that make our imprint on climate a little more long-lasting than I certainly realized until I began working hard on this a few years ago. And I'm also going to cover a second topic, which perhaps is more, most relevant because of this talk here in Mexico, and that has to do with the emergence of the human fingerprint on today's climate. And I'm going to show you that low-latitude countries like Mexico are beginning to experience changes relative to the variability that simply are far larger than what we see at higher latitudes. So those are the things that I'm going to be focusing on. And to start out, I think it's always very useful to remind ourselves of how extensive our observations of the warming of our planet really are. It's really quite inspiring to see that measurements extend over such a broad region of the Earth. We can show how much the planet has warmed since 1900, and you can see it's extremely widespread. There's a very few regions where there's a slight cooling, but they're by far the exception. The overwhelming majority of the Earth is warming. And go ahead and globally average that data, you get something. Number of different groups have done this kind of analysis, and they We all get pretty much the same thing, with quite significant warming in the early part of the 20th century, followed by a period when cutting in and out no matter what I do as far as my angle relative to it goes. All now, and yet sometimes it's there and sometimes it's not. So I'm not quite sure how. You have the handheld microphone. I'd be happy to just hold it. That might be easier. How's that? That's better, I think. Okay, so the period in the 60s and 70s when we saw less warming was one that was characterized by a lot more particulate matter in the atmosphere. The same sort of phenomena that you see here in Mexico City when you have such bad pollution events was a lot more widespread at that time, particularly over the United States and Europe. And it was actually enough reflection of energy out to space to probably account for a large chunk of this apparent lack of warming or even a slight cooling. Since the Clean Air Act was enacted in the United States and the European countries cleaned up their air as well, the emergence of the warming signal has become much clearer. And if you go ahead and average the data over the whole 20th century, it's about 3/4 of a degree warmer than it was in 1880. So that's quite a significant change. If you look at the warmest years, and I apologize for not having the last two, this is actually an older slide, but I do have an updated version that I forgot to swap in. But nevertheless, what you can see is that there's a remarkable sequence of the warmest years having been almost all quite recent. Most of us have to go a long way down on this list before we find a year that perhaps we weren't alive for. And what that tells us is that we are living in the warmest period in the instrumental record. So temperatures have been remarkably warm in the last 25 years. Well, it's sometimes suggested that the data are incorrect because of urban heat island effect. And of course, we all know that the interior of cities is warmer in many cases than the surrounding regions. But the data can be corrected for that, and that's been done quite carefully. If you don't want to rely on those corrections, there's an even simpler way to do it that I really find quite compelling that Jim Hansen published last year, where he looked at the night lights of the world, those wonderful satellite images of where the world has population centers that are bright at night, and identified places that were really pitch black, where there was absolutely no light. And even in the United States, you can find a remarkable number of such pitch black stations out in the really remote rural regions. And if you have a look at those data versus other ways of correcting the observations, I think it gives you a really good feeling. If you apply no adjustments to the data at all, you get warming that looks like this. If you adjust it for population, where you only consider points that are located in places with 20,000 people or less, you get a distribution that looks like that. And if you only use the nightlight stations, you get something that looks like this. So really, there's no real difference between the different sets of observations, because we really do know how to correct it very, very well. So if you have a look at the trends in the three cases, they're clearly not affected by any kind of urban heat island effect. And it's also, of course, quite clear from the fact that you see strong warming, particularly in the Atlantic and in some very remote parts of places like Siberia, that the warming is not due to urban influences. It really, truly is a global phenomenon. Well, lots of questions get raised about these data sets, and I think one of the nice things that one can do is to look at independent measurements that also tell you that the world is warmer. One of the best forms of that are the glaciers of the world, which are in nearly all cases receding. So here's a typical one that extended down to, say, that point in 1912 and now is way up here. If you only saw this in one or two glaciers, you probably wouldn't get too excited about it. And certainly no single glacier can make the case. There are some exceptions. There's some places, for example, in Norway, where increased snowfall has outpaced the melting. But that's by far the exception. The overwhelming majority of glaciers on continents all around the world are in retreat. And the extent to which they are in retreat is very consistent with what we expect to see from the thermometer data. So here what I'm showing you is the temperatures inferred from the retreat of glaciers in various continents around the world. The black line shows you the thermometer record, and as you can see, not only are the glacier records in rather good agreement with the thermometer record, they also go back much farther, and they allow you to say that indeed, in 500 years, we haven't really seen an anomaly, a period when the globe was as warm as it is today. Well, why is this happening? The primary driver for the changes in the Earth's energy budget that are causing this climate warming is man-made carbon dioxide. We refer to carbon dioxide and other greenhouse gases as, if you will, forcing agents. They're forcing our climate to change because they're changing the energy budget. They're changing the way in which energy can escape to space. In the case of carbon dioxide, the increase in it is also acidifying our ocean, and I'll talk a little bit about that in just a second. But if we take a look at what carbon dioxide has done over the last 10,000 years, I find it really quite remarkable how constant it is for some 9,900 years in that record, which is derived from ice cores in Antarctica, combined then with the current data which we can get from flask samples. So literally, when there were those kind of creatures on the planet, we had about 270 parts per million by volume. And when the Egyptians built the pyramids, we still had about the same amount. When the Romans built the Colosseum, you get the idea, pretty much the same value. And it really isn't until the Industrial Revolution, when fossil fuel burning increased dramatically, that the amount of carbon dioxide increased in this way. Today's levels are about 30% higher than we've seen in not only 10,000 years, but actually more than 800,000 years from direct measurements. Well, there's another feature of carbon dioxide that's worth mentioning, and that is that even if we stopped emitting it, it would take a very long time for the man-made carbon dioxide to actually be removed by processes in the Earth system. If you stopped emitting suddenly tomorrow, and of course that's not going to happen, this is just an idealized case, what you would see, what you would see is some carbon dioxide would be taken up fairly quickly over timescales of a few decades. That would be going into the biosphere, into trees, into plants, into soil, and particularly into the surface ocean. But those sinks for this gas then saturate, and the longer term becomes much, much slower. So here's the first 100 years. And then when you can't take up any more carbon on land because you've grown as many trees as you can grow, and you can't take up any more carbon in the surface ocean because it's become saturated, now you've got to, if you're going to remove more carbon, you've got to transport it down to the deep ocean, and that takes a lot longer. So the next 1,000 years have a much slower removal. And then the next 10,000 years, you're still removing it very, very slowly. In fact, it's going to take more than 100,000 years to get rid of all the carbon. So there's no one process that removes the carbon dioxide that we've put in. There's a sequence of sinks, and only a few of them act quickly. Those sinks saturate, and then it gets slower and slower and slower. So let me say just a little bit more about this unique property of carbon dioxide. As a chemist, I find it really interesting how different its behavior is relative to the removal of, say, all of these other chemicals. Other things like methane or the chlorofluorocarbons or N2O all get removed if we stop emitting them with a time scale that's exponential and defined by a well-defined removal process. In the case of carbon dioxide, as I've already shown you, that's not what you get. You get some removal that's rapid, but then much, much slower. And interestingly enough, a key reason for that really has to do with the same thing that leads to ocean acidification, and that is that the carbon dioxide dissolves in seawater, but in doing so it makes a proton and the bicarbonate ion. This then is a buffered solution, so you can only take up so much CO2 when that equilibrium is reached. The only way to drive more carbon dioxide out of the gas phase and into the seawater is to add carbonate to the system, and the carbonate is going to have to come from rocks on land, and it's associated with silicate weathering, actually. So this is going to be clearly a very, very slow process because it takes a long time to break up a rock. Okay, so let's then take that experiment just a little bit farther, and we did this in a study that was published in PNAS in 2009. We had a follow-up study in 2010 that talked in a lot of detail about the mechanisms. I just want to very briefly summarize here for you what would happen not just to carbon dioxide if we stopped emitting it, but also to the warming that it has produced on our planet. So we did this using an Earth model of intermediate complexity. That's a global model, but it's one that typically is at quite low resolution. You can sort of think of it as being like yesterday's global circulation models. It has does have different levels, 14 different levels in the ocean and a crude ocean circulation. So in some ways, it does simulate the Earth system, albeit at a very, very reduced resolution compared to what the best global circulation models can do today. But by virtue of that very low resolution, you can run it over very long time scales. And here what I'm showing you is what would happen to carbon dioxide and to the surface warming that it produces, not just over 100 years, but literally over 1,000 years. So the top shows you the different cases that we ran where we increased the carbon dioxide to, say, 450, 550, 650 parts per million. Remember, it's at about 390 today, and 270 was that, Egyptian value. And if we were to stop emitting at any one of those points, what we would see is that slow decay that I talked about in CO2. But what would happen to the warming is really interesting. It basically stays almost completely flat for just about 1,000 years. Well, I'm going to tell you a little bit more about the reason for that in just a moment. I just want to emphasize that when I say that it's largely irreversible, I do that recognizing that there are geologists in the audience for whom 1,000 years is just an eye blink. That's not reversible to a geologist. So when I'm saying that it's irreversible for 1,000 years, I recognize that on Earth system timescales that's relatively short, but it's pretty long for human civilization. A lot happens in 1,000 years. So on human timescales, I would have to call this largely irreversible. So every year of warming that we're producing essentially takes a time scale of civilization to be reversed. Every aspect of climate change that would be linked to that warming, such as changes in rainfall, changes in snow cover, etc., would also be largely irreversible. How could we get out of this? Well, perhaps by geoengineering, and there's going to be a talk tomorrow on that topic. But of course, we don't have any such mechanism to put reflective mirrors in the stratosphere or start actively removing carbon. We don't have such mechanisms in hand. So until we do, I think we have to think of this as being largely irreversible. And there are several reasons that the irreversibility happens. A key one, though, which is pretty simple to understand, is the incredible thermal lag that the ocean represents on our planet. So as we're pumping carbon dioxide up Heat is going down into the ocean. Most of the heat, almost all the heat actually, goes into the ocean. And as you know, the ocean, the water has a much higher heat capacity than the air or the land, and so it's a thermal inertia on the system that is massive. And that's a primary reason for the irreversibility. The other one is this slow removal of the gas itself, as I've already mentioned. So those two things acting in concert is what gives you this kind of behavior. Well, here now I've shown you the same parts of the problem, but I've also added the thermal expansion of the ocean on, and that is a way of looking at sea level rise due to the fact that hot water must expand, and that's a basic law of physics. In addition to the expansion of the hot water, we expect to see ice on land melt. Ice on, say, parts of Greenland and parts of Antarctica may very well contribute to future sea level rise. I'm not including that here. I'm just talking about the sea level rise due to thermal expansion of the ocean. And I think the key point that really is of concern here is the fact that the sea level rise goes on for many, many hundreds of years. So if you were to stop emitting CO2, the temperatures would stay, the air temperatures would stay about the same, but heat would still be being pumped down into the deep ocean the whole time that the carbon dioxide and temperatures were elevated. And the result of that is a continuing and very, very slow sea level rise. So what this is saying is that even if we were to continue to use fossil fuels until we run out of them, which might, for example, happen this century, the carbon dioxide that we would have already emitted would have, in a sense, committed us to a future sea level rise that could be quite large. For example, if we went up to 1,200 parts per million and then stopped emitting, we'd have over 1.5 meters of eventual sea level rise just from thermal expansion. And to that, you'd have to add the potential for ice melt. So we're making a decision in this century that's going to affect the geography of our planet for the entire millennium, for the next many hundreds of years. Places like, low-lying places like Tuvalu and Bangladesh, the decisions are being made right now about whether they will still be here in 500 or 1,000 years. Okay, well, let me talk a little bit about variability locally and globally. Pretty much everything I've talked about so far are global averages. And I just want to look under the hood a little bit. This is the January warming trends on the grid points where data are available, quite extensive, lots of places with warming. If we have a look at, say, one of those grid points in a remote spot in Canada, we see an upward trend, but we also see an awful lot of variability. So we're having warm summers. Actually, these are Januaries. I'm sorry, I'll show you some summer data in just a minute. We're having warm Januaries and cold Januaries in Canada. The fact that you may have a warm one doesn't mean that global warming is happening. The fact that you have a cold one doesn't mean it's not happening. There's a trend here. It's very similar to what we expect to see from models, but the average person would have a hard time being convinced by this in some sense, because they would say, well, you know, it's within the variability. And I think that also means that things like the ecosystem will have perhaps an easier time adjusting because it's already adjusted to the ups and downs from year to year. Australia, pretty much the same sort of thing. If I pick a point near Paris, the same kind of thing. Point near Denver, the same kind of thing. It's only when I average across the whole world that I get this kind of very clear global warming signal where now the trend is larger than the interannual variability. So it's the power of averaging over space and time that gives us the global warming signal. Why is it variable? Well, there are a number of reasons, but the simplest one is just the fact that fronts, particularly in the winter season, are active in moving air from one place to another. So cold air can come down out of Canada into, say, the United States. That makes it colder here. It also makes it warmer typically over there. So if we go ahead and average over the whole region, we don't see much of a change, but locally we see a very large change because this Canadian air is suddenly making parts of, say, Oklahoma look quite cold. So the averaging over space and time is absolutely critical to deducing any kind of meaningful climate change in most places, but not all places, as I'm about to talk about. So basically, I've begun to become very interested in this issue of variability and, if you will, the noise on the signal. How hard is it to see the climate signal as distinct from the noise? I think it's natural for people to be skeptical about whether or not things are changing when there's a lot of variability in the signal. It's easier, I think, to understand a signal that is less variable. So we began looking for where on our planet we would see the biggest signal. And the first step in doing that was looking at the signal itself. So this is a map of the warm months, so the 3 warmest months of the year, which in the northern hemisphere would be June, July, August in most places, not everywhere, but most places. In the southern hemisphere, typically December, January, February. But at every grid point, we use the 3 warmest months. And as you might expect, the places where things have gotten hot, a lot of them are at high latitudes, particularly up in the Arctic. This is what the models would suggest the change over the 20th century should have looked like. And there's a fair amount of similarity to the observations, although it's obviously not perfect. It overlaps in many places. But what if we look at the noise? We've looked at the signal. Now let's look at the noise, at the variability from year to year. And what we see there is actually very interesting. The largest variability is at the higher latitudes. And that's related to what I was talking about earlier with the whole issue of fronts and gradients and the effects of circulation. The lowest variability outside of the El Nino regions is in the deep tropics. So places at low latitudes have the least variability. Again, that's true in the models. It's also true in the observations. So the low variability in the tropics then has to be kind of a clue that maybe the place where the signal to noise is going to be largest might indeed be there. And that really surprised me when we started this work. I thought the place with the bellwether for climate change, as it's sometimes referred to, would be the Arctic. That turned out not to be true because of high variability. And as you can see, the place with the highest signal to noise is indeed low latitudes, including some parts, obviously, of Mexico and a little bit of the southwest U.S. So I think this is a very interesting result, one that as it kind of begins to then raise the next question, does this mean that places in these regions of low signal to noise are already seeing a discernible signal? And according to our analysis, many places actually are, even at the grid point level. If you have a look at, and I'm sorry I don't have a Mexican point on here, but you can see that Mexico would be about the same as the point that we did pick here in South America. If you look at the warming trend over the 20th century and the variability, the noise on that trend, you can begin to see that the summers in that region are not like the summers of the past. The hot summers are hotter than they've ever been. The cold summers are not as cold as the coldest of the past. And that isn't really true if we say, look, in America, in the US, although we do see a trend, the hottest summers are still right now, still within the hottest summers of the past, and the coldest ones are still pretty much within the coldest ones of the past. So it's going to have to get a little hotter before the signal is really going to emerge clearly in the United States, but it's already emerged in Mexico, where you're seeing hot summers that are hotter than they've ever been. And of course, as you can see here, Africa and parts of South Asia are places with even stronger signals in that way. So we did this analysis realizing that it might tell us something a little different than what we expected, and we learned a lot from doing it. We've also begun to look at the issue of precipitation. In the case of rainfall, at least so far, what we're finding is that the signal has not yet really emerged from the noise at the local scale anywhere, although it probably has regionally. I want to emphasize that in what I showed you here, I'm really talking about every grid point in these places. It's not just the averages over regions, it's the local values. Well, who's emitting all of this carbon dioxide? This is now turning to the human side of this problem. If we have a look at how many tons per person per year are emitted in different countries, the United States, my country, is right there at about 20 tons per person per year. Places like Mexico are much lower at more like, I think about 5 or 6 times less than we are. So it's really quite interesting how there's sort of a club of big emitters, then the Europeans at about half, and then a number of other countries. And of course, we look at this graph and we often look at these countries down here on the bottom and we just say, well, they don't emit very much, do they? And I thought it would be interesting to actually try to figure out how much they really do emit, those countries on the bottom, compared to, say, the average American. So I did the plot somewhat differently. I took the ratio of the US per person emission to that of the different countries. So what this is telling you is that the average American emits 1,000 times more than the average person in Chad. The average American emits 200 times more than the average Ethiopian, about 80 times more than the average Kenyan, about 5 or 6 times more than the average Mexican, etc. And that to me is a very remarkable and surprising and informative plot. Perhaps it shouldn't be surprising. People who live like this are obviously emitting a lot less carbon than people who live like this or people who live like that. If you go ahead and average across the entire world, the 6 billion people who are now in the developing world emit about 5 times less CO2 per person than the 1 billion in the developed world. So the important issue before us is, what about those people's future? As they develop, if people develop using the same carbon in the same way as the developed nations did, the planet's going to get very hot indeed, and I think it will have some very important implications for world peace and security. Especially as the signal to noise in the tropics, which I've already shown you has been emerging in a remarkable way, continues to grow. So the countries that are doing, if you will, the least damage are seeing the earliest signal. You often hear people talk about the vulnerability of developing countries in climate, and by that they're really referring to the fact that in developing countries there may not be as much money to help adapt by doing things like, doing more firefighting or managing your water differently or whatever. But here I'm saying that there's a vulnerability which is part of the physical system. It's that as it happens, the tropical countries are seeing the largest effect, the earliest, relative to the noise of natural variability. And there's no reason why this graph should have come out the way it does, but what this is showing you is the CO2 emissions per capita as a function of the temperature signal relative to variability, where the red points are the developed world countries and the black points are the non-Annex 1 countries. And as it turns out, almost all the red points have high emissions and low signal to noise, and almost all of the developing countries have low emissions and very high signals. So I think it's important to think about the implications for people, the fact that the way the climate is changing, the type of human suffering that's already being experienced, some of which is probably due to our combined activities, is mainly being driven by the developed world, and yet most of the impacts are in the developing world. Well, I wanted to leave a bit of time for questions, so I'm just going to quickly talk about a couple of other things. What would it take to stabilize the carbon dioxide in the atmosphere is a question that is often asked. And it's easy to get the answer on this one wrong. If you, this is just showing you the CO2 again over 1,000 years, what it's actually done and how it's increased. I want to just give you a little hint here. CO2 in the atmosphere is a lot like the water in a bathtub. So you can think of the amount that we're emitting as being like the water coming in through the faucet. the amount that the physical system can remove through things like dissolving in the ocean and taking it up in trees is the drain. The emissions by human beings, and I'm sorry this is a slightly different scale, but since 1750 the emissions have done this. So if you ask most people what it would take to stop the carbon from increasing, in other words, let's say we wanted the carbon to just stay flat at 300, which is where it is now, the emissions have done this, what would we have to do to stabilize the carbon? Most people would say you would have to do that, just keep the emissions constant. That's not the right answer, and the reason it's not the right answer is, again, easy to understand in the context of a bathtub. What's happening right now is that the amount we're putting in is about double what's being taken out through the drain. So if we were to just keep our emissions the same, the water in the bathtub would still rise. It just wouldn't rise faster than it has been rising, but it would keep rising. So if we want to stabilize the water in the bathtub, we're going to have to reduce our emissions by about 50% so that the amount coming in through the faucet matches the amount going out through the drain. It turns out that actually only does it for a few decades. Eventually you'd have to reduce emissions by 80% and more for reasons I don't have time to go into. But you get the picture. We've already driven the system way out of equilibrium, and getting back to a different state would take a major change. And don't forget what I've just told you, that 6/7 of the people on the planet are currently emitting 5 times less per person than the other 1/7. So if they emit as the rest of the planet, or as the developed world emits, what you'd end up with is something more like this, and a very, very rapid rise in CO2 and in temperature. And that's really the essence, to me, of the sustainability problem and why climate change is such a problem. Well, another issue that, of course, we're mostly aware of is the fact that we've all made commitments to keep emitting carbon for a good long while. If you own a car and you're going to keep it for 10 years, that's a carbon commitment. If you own a house, or if you get your power from a power plant, that's a carbon commitment of maybe 50 years. So what's coming to our climate system and how fast? We kind of have to think of this as being like driving. You really have to be aware of what's in the mirror. And the bathtub problem, to me, is a big issue in the mirror. The international issues and the conflicts that are likely to develop and worsen as it becomes really clear how big of an issue this is, and the emergence of altered climate states, specifically in the lower latitudes, is, I think, a coming issue. We all have lots of stuff, commitments to stuff that we want to keep, and what we're now doing will last for more than 1,000 years, so any choices that we make are long-term choices, so we better be sure about what we're up to. It's important to think about the emissions not just per capita but also by country. So that's what the US emission total across the whole country has done. That's what Chinese emission has done. Chinese people do emit about 4 times less per capita than the average US person, but there's about 4 times more of them. So as they've rapidly become wealthier and begun to emit more, they've actually surpassed the US in terms of total emission, but they're doing it with 4 times more people. So that's an interesting issue to think about, and there's a few other countries. So I just want to not forget to say that my carbon footprint is really big. When I flew here, I used up about as much carbon as the average Kenyan does in a year, and I fly a lot. My car is actually one of those, so I don't emit that much driving, and I actually don't drive that much. I take the train a lot, but I do fly a lot. And so I emit about 140 tons per year, which is a lot of carbon. So I'm well aware of how hard it is to reduce your carbon footprint. What really matters is what we do next. I talked about the commitments that we already have, and what this is showing you is the future emissions from existing infrastructure versus future infrastructure. So the colored part is the past and future emissions from the stuff we already have. If that was all we ever had, we'd end up with about somewhere between 1 and 1.4 degrees of global warming. because it would decay away, and we'd replace it presumably with carbon-free technologies. The future infrastructure yet to be built is somewhat uncertain, but it's really all those planes, trains, automobiles, power plants, homes. It's the emissions from that will give us a very large amount of warming by 2100. So our choices about what stuff we're going to build are really what matters. I want to save a couple minutes for questions. I just want to mention the whole concept of wedges of mitigation options. And these are just examples of such wedges. There are others that could have been on here, and I'm not trying to advocate for any particular one. But if we wanted to stabilize the carbon dioxide levels at where they currently are, we need about 12 of these wedges. And what they represent is a savings of a gigaton per year by 2050. So we need 12 of those. We could get one from, say, reducing deforestation. We could get one from having 50 times more wind power or 700 times more solar power. We could get one from everybody driving 60 mile per gallon cars or having better buildings. We could get one by doubling the current capacity of nuclear on the planet. So these are just examples of the kinds of things that could do it. And the main point is that there are no silver bullets. There's no one thing that's going to solve these problems. But there is a lot of silver buckshot, and certainly technology development is going to be critical. Decarbonizing the energy supply is absolutely key. And thank you very much for your attention. I think we have a few minutes for questions.
Muchas gracias. Mi nombre es Daniel Hernández. Y el aumento, sin duda, del nivel del mar es un escenario catastrófico. Pero, ¿qué tan probable es que con el derretimiento de los polos, las corrientes marinas se detengan y esto provoque una glaciación, que sería un escenario todavía más catastrófico? Gracias.
Okay, well, that's a very interesting question. Will the changes in meltwater coming off of, say, Greenland and Antarctica change the ocean circulation? The answer is that there is pretty good evidence that it will to some degree. Will it reverse it entirely? Most of the studies that have been done on that with the best model suggest it's very difficult for, the Gulf Stream to come to a dead stop, and the kind of picture that was painted in the movie The Day After Tomorrow, it's just a movie. It's not really what we think is going to happen. But a reduced rate of circulation and the meridional overturning indeed probably will happen. Maybe already is happening. There's some debate about that, but some studies have begun to actually say that louder and louder. The biggest impact of such a change is probably ecological. It would have a massive effect on the ecology, particularly in the Atlantic. So indeed, that is an issue.
Hola, mi nombre es Isaac, vengo del Departamento de Física del CIMBESTAB. What would you say about those scientists that don't think that there's no affection about... Hago en español. ¿Qué piensa de los científicos que apoyan la teoría de que debido a los cambios, a los ciclos térmicos propios de la Tierra y del Sol, en realidad el cambio climático no es producido por, digamos que no es antropogénico?
Yeah, we could talk about the sun a little bit. Actually, if I could have my slides back on, I do have a quick slide that would help to address that. I think that the key point to remember about the sun is that it actually has not gotten brighter in the last 50 or so years. So it's pretty hard to make an argument that says the sun is responsible for what's happening. If you have a look at how bright the sun has been, and we have pretty good measurements of that going back at least to 1978, you see an 11-year cycle in that, which has to do with things like the magnetic field on the sun and how it modulates the amount of energy escaping from the sun's atmosphere. So the 11-year cycle is well known, but there is no trend in it. You know, you can actually see the 11-year cycle probably weekly in the data, but it's very hard for me to imagine that the sun is the cause of this. So I think the evidence for the sun is frankly pretty weak. It doesn't have the right kind of time behavior. It also doesn't really match the latitudinal distribution of what's been observed. So, you know, the sun could be playing a minor role, but I don't think there's much evidence that it's a dominant role.
Bueno, muchas gracias. Mi nombre es Ana Cristina Ramírez, vengo de la Universidad Michoacana. Le agradezco por una plática que ha resultado estimulante y preocupante. Me gustaría conocer su impresión acerca del dato que arrojó un estudio del 2009, me parece que de la ONU, de que la crianza de ganado, la crianza intensiva de ganado y la producción de gas metano está contribuyendo con el 18% de estos gases.
I guess the question is about sources of methane. And indeed, cattle are a significant source of methane. So is rice, so is mining, so is waste. So it's really those four things that are responsible for the increases in methane. Methane's the number 2 greenhouse gas behind carbon dioxide. Its radiative forcing is about a third, roughly as large as the radiative forcing due to carbon dioxide. It's a lot shorter lived. It only lives for about 10 years in our atmosphere, so it isn't a problem for a millennium. If we were to stop raising cattle or find smarter ways to feed them so that they wouldn't emit as much methane, then the problem would not last for thousands of years. It would last for decades. So methane certainly is a problem, and indeed cows are part of the problem.
Yeah, Dr. Solomon, what's the degree, it's kind of a question close to the one my mate just did. What's the degree of certainty that we have, and the evidence we have, that that the global warming is 100% caused by anthropogenic causes? What's the degree of certainty?
Well, I mean, you could never say 100%, right? I mean, I think there is an element of natural variability that could be involved. The best evaluations of this problem have argued that we are about 90% certain, so 9 chances out of 10, that at least half of what's happening is man-made. But to argue that it's 100%, you know, that's a big ask. That humans are contributing, I would say we are, in my opinion, 100% certain humans are contributing something. You know, but you know, to say that it's 100% is impossible. And you know, that would never be true in anything. I mean, you know, I'm reminded a little bit of people who argue that they're not going to be concerned about smoking and lung cancer because they've heard that the cousin of a friend of theirs got lung cancer and they didn't smoke. You know, so you know, it must be that scientists aren't sure that smoking causes lung cancer. I mean, personally, I just wouldn't take that kind of a line of argument. But you could never say that you're 100% sure that all of it is due to human activity. But most of it, I think, very clearly is. And I should add that a big part of the argument behind that has to do not only with the global warming itself, but also with the pattern of what's being observed, both in altitude and in latitude. It's remarkable how well the pattern fits with what we expect from the greenhouse gases being the major cause. And if it were solar, it would be much more difficult to get that. Certainly, for example, the cooling that we see in the stratosphere would not happen if the sun were the cause of the warming at the ground, because the sun has to pass all the way through the stratosphere and down to the ground. So it would give you a different vertical structure.
Me llamo Mauricio Schoiget del Departamento de Hombre y Su Ambiente de la UAM Xochimilco. I have three questions. I imagine you probably know the suggestion of James Hansen of decreasing the CO2 content in the atmosphere by making charcoal, right? You call it charcoal from vegetable waste, okay? Second
Talking
question.
about biochar, people have talked about something called biochar, where the idea would be that you would turn waste agricultural products into charcoal. Yeah, that's one mechanism that's been suggested as a way to reduce the carbon.
You think it's viable? You think
I'm not an expert in all these different technologies. I'd be surprised if it gave you a wedge, but maybe it'll give you part of a wedge. It's not going to solve the problem. I continue to argue there's no silver bullet. Could it be a piece of a wedge, or maybe even a whole wedge? Possibly. But I've heard a lot of arguments about the permanency of the biochar suggestion. That indeed, you can make charcoal, but on the other hand, what are you going to do with it? You put it back in the ground, it may come right back to the atmosphere. The process of making the biochar uses energy, and so you get into all kinds of issues there. It's certainly no silver bullet. Let me put it that way.
I have a second question. Would you say, given the amount of uncertainty, you should consider it more an ethical question than anything else, and therefore the most radical measures would be justified because of this? What do you think of this? That's
an interesting question. I personally have begun to think about the ethics of the problem much more than I used to. And I'm particularly thinking about it because of this work that I've done recently on the issue of signal-to-noise. And if indeed it turns out to be true, which I think ours isn't the only paper pointing this way now, that the most clear signals relative to variability are emerging in the countries that are contributing the least to the problem, namely low-latitude countries like parts of Mexico. To me, that's an ethical problem. I do agree with you. We need to be talking about the ethics of this problem a lot more, not just about the science. It isn't going to make the discussion any easier, that's for sure. The discussion's already difficult enough. On the other hand, it's clear that it's a human decision that is so fundamental to everything about our way of life and our economy that I don't think we can avoid the ethical side of the argument.
Well, last, you might have heard of several scientists who suggest that global warming might drive humans to extinction, or at least to a brutal retrogression. Do you have any comment on that?
I guess that's a little bit too sweeping for me. Yes, I don't. I think we're pretty smart and resourceful, and we're not going to be going extinct. I think we might make things a lot harder, and I'm not going to say that some individuals won't perish. I think people will die as a result of it. One of the things that worries me the most is actually the increased incidence of fire. The fact that as the planet gets hotter, it's pretty clear that you will see more and more fire. And you know, fire is scary stuff. It does kill people. So do floods. All of those things have the potential to kill individuals, but I don't think the human race is going to go extinct.
Soy Laura, estudiante de matemáticas, and I want to ask you something. Despite all these talks you and other scientists say about climate change, there's a lot of people who don't believe in it or don't want to believe in it. What do you think would be a good way to handle this in the media, to convince people that it is actually happening and we all have to do something, not just some people and not just the rich people?
Well, I guess the first thing I would just say is I don't think it's a matter of believe or not believe. I mean, you know, you don't believe or not believe in the law of gravity. If you're a scientist or even, you know, a person with any amount of scientific education, you know that, you know, gravity exists. And, you know, the basic physics of warming is pretty clear to me. So I think stopping talking about it as a belief would really be a first step that would be really helpful. On the other hand, and so I'm going to maybe sound a little bit contradictory in some sense, but if you listen carefully, you'll see that I'm not. On the one hand, we have to separate the science from a belief system. On the other hand, we have to also recognize that this issue makes people very uncomfortable, that it does raise issues of ethics, as we've just discussed, that it raises issues of economics. And so I think separating those two things, separating our understanding of the phenomenon from how you feel about the fact that if you take it seriously, we're going to make a decision one way or the other about what to do about it. And one way to decide is not to do anything. And, you know, let the planet get very hot and see what happens. But the separation of the human issues and the emotional issues from the scientific issues would be a great step. And I think we can work in that direction. I usually, when I run into people who are very confrontational or very negative about it, I really try to get them to talk about how they feel. You know, why do you feel that way? I mean, let's not talk about the science right now. Tell me why you feel that way. Let's not debate, you know, is the data right, or, you know, have people done the right calculations, or are the models imperfect? Tell me how you feel about it. And usually that actually is very illuminating. They'll say things like, well, you know, I feel like it's just going to be too expensive, and I'm scared because, you know, I might lose my job, and, you know, I'm really feeling insecure, you know, or they hate. And, you know, unfortunately, this is something that we see a lot of. Some people really hate international agreements in the United States. You run into a lot of people who just, they're sort of isolationists by nature. They don't want to be involved in any agreement. So the idea that this would be some big international agreement, they just hate it. So, okay, let's talk about why you hate international agreements. Let's not smear that with the science, you know. That's the kind of approach that I like to take. Let's do it in steps.
Ok, entonces, antes de agradecerle a la doctora, me gustaría recordarles que mañana tenemos un mini simposio para discutir algunos de estos temas que ella tocó. Empieza a las 10 de la mañana, no recuerdo en qué sala.